Hello everyone, welcome back to the latest lecture session. Quick recap of what we have been up to. We talked about material balances or mass balance, right, in the context that of wastewater treatment. Obviously, in environmental engineering, or an environmental engineer is going to apply mass balance in his everyday life too. We discussed that in some detail. We looked at the kinetics too, because we have to look at the rates of formation and rates of loss when looking at mass balance, right. And then we started looking at various aspects in terms of quality and quantity of the water. Yes, that is going to be coming into the wastewater treatment plant. In that context, we looked at 4 or 5 major parameters. What were they? Let us just have a quick recap. BOD and COD, which more or less look at the organics. We are trying to measure the organics that exert an oxygen demand, let us say, right. And then I believe we looked at suspended solids and total dissolved solids, right. And we also looked at pathogens, those that can, or microorganisms that can lead to formation of disease, right. And I believe these were the major categories that we looked at. So, in the treatment plant, what is it I am trying to remove? When I say I am trying to treat my wastewater, what is it that we are trying to remove, right? I am just trying to what do we say, classify them, because the kind of process that you choose will depend upon the kind of what do we say, not parameter, material that you are trying to remove here. So, we have grit, right, and other heavier particles. Grit, think of your coffee beans, sand or such that comes in along with the rains, or coffee beans, roasted coffee beans that you use and sometimes dispose into the drains, such, we have grit. And then we have some relatively finer suspended particles, right. Grit, how do we differentiate that from the suspended particles? We can differentiate by the fact that grit, or the particles which we classify as grit, are relatively heavier, and thus are going to settle, let us say, at an order of magnitude greater than that of the suspended particles. Suspended particles, we are going to have both organic and inorganic, the fraction will vary. And then we would like to also remove the dissolved solids, which is mostly the organic compounds, that is mostly organic content. And where is this organic content coming from? It is my feces or urine, let us say, and that we are going to call as the waste, or our waste, and this waste is the food or substrate for the microbes, right, for the microbes. And why do microbes want to use this? Because they want to use it for their own cell synthesis, right, and for energy needs and growth. Let us say you are going to want to multiply, same case with microbes, they want to thrive and multiply. So, from this redox reaction, where the organic compounds are oxidized in the presence of oxygen, they are going to gain the relevant energy here, right. And then we want to look at pathogens, or we want to take care of them, so that the treated wastewater does not have a lot of pathogens, right. And one aspect to note is that the conditions we create in this particular process, or during this process, typically leads to decrease in pathogens. The pathogens can't survive the kind of complex microbial environment that we have out here. Other than that, we are still going to look at removal of pathogens by disinfection. So, what are we going to look at in general? Heavier particles, which are typically suspended, and relatively smaller but suspended particles, and then dissolved particles, and then pathogens. Let us see which unit process in our treatment, which of the unit process in our treatment plants correspond to each of these relevant what do we say, particles or parameters we just discussed. So, here we have what do we say, 4 major classifications or unit process. One is the headworks or the preliminary treatment, preliminary. The other one is primary treatment or primary settling, primary treatment. The second one is called secondary treatment or the biological treatment, and the last one is disinfection. So, here we are trying to do or remove, pardon me, grit, right, the coarser particles and such, sometimes finer suspended particles, but typically you do not do that. But why do we also say headworks? We call that headworks because how is it that sewage is flowing from your home to the relevant wastewater treatment plant. Obviously, if it's a very hilly area or if there are great undulations in the terrain, that's a different aspect. But in general in India, that's not the usual case that is encountered, right. So, here you are out here, and typically the wastewater treatment plant is constructed at a lower elevation. So, by gravity your sewage is going to flow from your particular home to the STP now, right, to the sewage treatment plant. So, for this flow to occur, as in from the flow or the wastewater to go from headworks to primary settling, then to secondary treatment, and then to disinfection, right, you want to have a particular flow, right, or you need the flow from one unit process to the other, and that you typically want to achieve by gravity. So, what do you need to do here? You are going to pump it up to a certain head or height, and there from each unit process to the other you are going to have flow by gravity, right. So, that is why we call it headworks, because you are going to have the relevant pumping, and you are going to have removal of the grit and coarser particles and those particles that can mess up your mechanical instruments, the machinery and such. And in primary settling, we are going to remove the relatively finer but suspended particles, right. Here we are going to remove the suspended particles, preliminary treatment, not preliminary, pardon me, primary treatment, right. And here in secondary, which we refer to as biological treatment, we are going to remove the dissolved organics. Mostly the focus is on dissolved organics, let us say, right, dissolved organics. Here in disinfection, what is it that we are trying to take care of? The pathogens, yes. So, that is what we have. More or less most wastewater or almost all wastewater treatment plants are going to look at variations of what we just discussed. Sometimes you will have tertiary treatment when we are looking at removal of nitrogen or phosphorus, right, the nutrients, or when you are trying to look at further treatment of your effluent from the secondary treatment, right. So, that is something to keep in mind. Let us just have a quick look at the relevant unit process in greater detail. Headworks and pre-treatment. So, what are we trying to do? We are trying to prepare the wastewater, right, such that it is fit to be treated by the relevant unit process downstream of the headworks, right. You are going to remove the bigger particles, people throw plastics, rags, whatnot comes into the relevant drains, right, or through the drains, and you do not want them to clog or cause abrasion on your mechanical or moving parts and lead to wear and tear, right. So, you want to prepare the wastewater and also increase the head available so that the flow can go by gravity. So, you are going to have pumping stations or lift stations, right, as I mentioned, we just discussed this. Bar racks to remove the relevant rags, sometimes toothpaste tubes and so on and so forth. So, coarser removal, let us say sometimes, then grit removal is also going to take place. We are going to look at that today, and then you will have primary sedimentation or primary removal, right, primary treatment. Here suspended particles are going to be removed. So, how are they going to be removed? We will look at that in greater detail, but again Stokes' law, more or less we are still relying on gravity to do the job, but we might add coagulant, so that the particles flocculate, form flocks and then settle down, right. But depends on whether or not you want to use that in your wastewater treatment. We will discuss why later. Then biological treatment. In biological treatment, as the name indicates, you need to have microbes, right. So, the microbes can be suspended in the water, yes, and there are different types of process which depend upon suspended microbes in the relevant wastewater. One is the activated sludge, which is relatively more engineered system, and the other is an aerated lagoon. You see that, you see the lagoons out here, yes, and you see the aerators out here, aerated lagoons, right. You see the air being supplied, but we are not really adding microbes or such. We let them people typically let them develop there. Though we are calling or classifying aerated lagoons under suspended growth, you will also have attached growth along the slopes and the bottom, right. Microbes will develop along the slope and the bottom. And then stabilization pond, yes, again you can have aerobic, similar to aerated lagoon. You can have different types of stabilization ponds, but the issue is that they require a large area, treatment efficiency is relatively less. Earlier people used to use them when land was plentiful or availability of land was not an issue, and also when, let's say, the concentration of wastewater was not very high and the flows were less. But with increasing industrialization and changing lifestyles, right, you have different or higher quality and quantities of wastewater being discharged, and these stabilization ponds don't really do the job anymore. So you can have aerobic, facultative and anaerobic. So they can be in series, or depending upon the depth of your pond, you can have aerobic, facultative and anaerobic, as in if the depth is relatively higher, let's say. So the top layer where you have more oxygen available because of transfer of oxygen from the gaseous phase to the relevant top layer of the water, it's going to be aerobic. In between out here, it's going to be facultative, and at the bottom where there is no oxygen, it's going to be anaerobic, right. Again, enough of that, let's move on. So attached growth, as in, you know that, let's say, sometimes you see the microbes growing on the walls of, let's say, poorly cleaned restrooms, or maybe near the canals or such, let's say the outlet of wastewater or such. Again, that's more or less attached growth, right. You have microbes developing on a media, let's say, or a surface, right, attached growth. So here we have trickling filter and rotating biological contactor, pardon me, and then we move on to secondary sedimentation. But in general, people mostly go for activated sludge process, and sometimes a combination of activated sludge and attached growth, but we will discuss this later. We are just looking at an overview. Again, here we are removing the grit, right. Here we are removing the suspended solids. Let me say just suspended solids, no need to say suspended solids. Here we are removing the organic content, which is mostly dissolved, right. And then after your particular activated sludge process, depending upon the kind of process that you use. For example, if it's activated sludge, you will need to have a secondary sedimentation tank, right, because the kind of microbes that are going to be formed, they form flocks and they are going to settle down. We will have a video and we will look at that soon. So as is mentioned here, usual with biological, but some ponds and lagoons do not have that, right, secondary sedimentation. And all this sludge, meaning microbes that have degraded the organics, what will they do? They are form flocks if we maintain it well, and because they are heavier, they will settle down, right. And this settled sludge or the microbes, what do? We bring it back to your activated sludge process where oxygen is pumped in, right. Why is it? As the name indicates, it's activated sludge. That's what you see, the microbes or the sludge that has settled down will be recycled back, because the wastewater coming in will not have enough microbes. So you need a source of microbes in your aeration tank for the redox process to go through at a faster rate, and that's why you have this particular microbes being recycled, right. So that's the activated sludge process, let's say, right, activated sludge process. Again, then disinfection, because out here, even though most of the pathogens will be killed in this particular aeration tank, you will still have some pathogens, and that's what you want to take care of by disinfection, right. And again, depending on the kind of disinfection that you are using, you either have to look at bringing down the disinfectant that you added, or need to minimize the disinfection byproducts, which I am going to label as DBPs, which are typically carcinogenic, right. And then sludge management, as in not all the sludge is going to be recycled. Mass balance, everything is about mass balance, we will look at that later. Depending on the mass balance, we will have to waste some sludge, and that sludge needs to be managed. Why is that? Again, microbes, sludge, considerable organic content. If you leave it out there, anaerobic conditions, it's going to smell, right, decompose, right, and septic conditions and such. So you have to look at it. What do you need to do? As we looked at it in the video earlier, we have to dewater it, and then stabilization, right, and such. So, we are not going to go into that in detail now, but again you have to also look at sludge. Depending upon the kind of plant, people can try to look at what do we say, energy recovery from this particular decomposition or stabilization of the sludge. Let us move on. So, sometimes as I mentioned, we will look at tertiary treatment. For example, I might need an additional level of filtration or removal of suspended particles. So, I can have an additional removal of filtration or coagulation and flocculation step after the secondary treatment or before too, depends, right. And granular activated carbon, as in I have activated carbon media that has a lot of pores and such. So, it provides good sites for adsorption of the relevant organic content, so that you can decrease the organic content of your effluent further. So, that is one way to do that. And then nutrient removal either by ammonia stripping, right, nitrification and denitrification, or then ammonia stripping, let us say, or phosphorus precipitation, right. You are going to look at that, we will look at that later. Then physical treatment, but in wastewater not really done, but again sometimes depending upon the quality of the wastewater. Or you can modify your particular secondary biological process such that you can achieve nitrogen and phosphorus or nitrogen and phosphorus removal. Again, these are minor modifications, let us say. Again, this is a UG course, we will not go into the design steps in detail, right. We will not go into the design steps in detail. We want to see to it that we spread awareness, certainly, but then we want to give out the principle and give you the fundamental building blocks such as mass balance, and let you know what are the relevant unit process and such, so that you can use them as and when required, let us see, right. So, headworks, in today's class I will try to cover these aspects, headworks or preliminary treatment, right. We will today try to cover preliminary treatment or headworks, right. Well, we will have to understand the goal. What is it that I need to do now? Not just the organic content, a lot of suspended waste, that is junk, plastics, right. A lot of it comes in, sand and silt comes in because we have open drains, right, or even if there is a combined storm water and sewerage network, you will have again a lot of silt coming in. You do not want this choking up your relevant plant, settling down in your preliminary or primary treatment or secondary treatment process, right. That will choke up your plant, let us say. You do not want that, right. As in, if I have a particular design for a particular volume, but I do not remove the sand out here during preliminary treatment, but in my primary treatment I need a volume of V. But what happens is that all the sand can end up, what do we say, choking, not choking, taking up valuable space or taking up the valuable volume by settling at the bottom, and then you are going to be left with a relatively smaller effective volume, and that is going to affect the time that your compound or the water is going to spend in that particular tank. So, that is an issue. Then pumping station, we discussed this, as in here is my house, and you know in general we do not use pumping stations for the sewerage network, but we let the sewerage network see to it that it flows by gravity to the STP. So, it is at a low point now, but for all the succeeding unit process I want the flow to occur by gravity. So, here I am going to pump up the water to a certain head or height, let us see, right. And another aspect which we are not going to discuss in detail is that, for example, STP is already out here, right, and some homes are here, some homes are here, right. This is where what do we say, holistic planning with respect to sewage treatment and such comes into play. So, you can either try to have pumping stations so that this sewage joins here and ends up at my STP and such, but again pumping stations for wastewater treatment I would say is not a sustainable alternative, really not a sustainable alternative, sustainable solution in the long term. Pumping stations for what do we say, bringing up the sewerage from one what do we say, network to the other, let us say, that is at a higher height, right. Again, flow measurement, why do I need to look at flow measurement? We will look at that. I need to know how much flow is coming because I need to be able to design the system. We will look at that. As I mentioned, we will have bar racks and screens, coarse screens and such to remove the coarser particles. Each step we are going to remove first the bigger particles, then the slightly bigger particles, and then the suspended but finer particles, and then the dissolved particles and such. You can see the steps obviously, right. And then grit removal, which we discussed. What is grit? What are we trying to do? And then some sedimentation fundamentals, let us say, because grit removal can be done by what do we say, or with the aid of gravity, right. Let us get this started now. So, goal of this headworks and preliminary treatment. Primary goal is to raise wastewater so as to allow free flow under gravity, and also prepare it for treatment by removing the grit or the particles that can, what do we say, mess up my machinery, right. I again do not want it to go into the stream, that is the river, it meaning the plastic waste and such. Other than that, I also do not want to have high maintenance in my particular plant, let us say, right. So, I need to look at preparing the wastewater for treatment. So, that is my primary goal. And some of the figures for which I might not give reference, some of the figures at least from with an Indian background, I took them from Dr. Kazmi, my colleague in IIT Roorkee, let us say, right. So, thanks to him for that. So, pumping station, let us see what we have. So, this is the pumping station, right. So, underground sewer is coming in, and this is the screens that we see, coarse screens typically before the pumping station, and then the sump well where the wastewater is being collected. I think you saw this in the video also, right, for IIT Roorkee sewage treatment plant. And then you have the probably the submersible pumps, maybe, yeah, probably the submersible pumps pumping the water up from the sump well into this particular what do we say, pumping mains or rising mains, let us see, right. So, that is what we have, a pumping station. But again, here we are not really talking about some of the what do we say, aspects we are going to discuss, but let us move on. Okay, so, when we are talking about pumps, there are two types of configurations. One is the dry well pump and the other is the one with just the wet well, but with the submersible pump. So, what is the difference here? You have two sections. One is the dry section, dry well, which contains your relevant pump and such. It has access to the pump, so easier to maintain and such whenever there is a breakdown. And the other one is the wet well or dry well pump. Dry wells will also have a wet well section obviously, but again we typically only look at the term dry well when trying to describe this particular system. So, wet well, from there this particular water is sucked in and brought up to the required head, let us say, right. So, this is the head that we are trying to increase, let us say, right, and we will look at this. Again, the other one is wet well. Here you see that we do not have a separate dry well system, and the relevant pump and such is more or less a submersible pump. That is what you see out here, and whenever required it is hoisted up, right. Here typically maintenance and such seems to be low, but whenever maintenance is required, then that is going to be a concern. But one aspect is the costs are relatively less or seems to be relatively less with wet well submersible pump systems, let us say, and that is what at least we see in India most of the time now, right. So, that is something to keep in mind. Let us move on. So, again submersible pump system in what do we say, greater detail, let us say. Submersible pump out here, right, flush bottom for the relevant flushing as and when required. You have the relevant what is this now, heights and such that are given. But again, you can look at the CPH EEO manual for such figures now, right. So, I will not go into this in great detail. So, here is the ground level as you can see, right. Let me see where it is that, okay, this is the chain pulley, that is one aspect to keep in mind. Overflow pipe, fine manual screen, right, and that is the relevant. Okay, here is the incoming sewer pipe, and I have the manual screen out here. And then this pump is going to lift it up to the relevant level out here, right. Here is the inlet and here seems to be the outlet, let us say, right. So, that is something for you to keep in mind. Okay, let us move on. What are the types of pump? Typical one, Archimedes screw, right, pretty simple setup, relatively less moving parts, remarkably easy to maintain, and then non-clog centrifugal pumps, right. So, let us look at what they are. So, non-clog centrifugal pumps, one is the horizontal axis driven with the impeller rotating in the vertical plane, impeller rotates in the vertical plane. The other one for which we have the figure here seems to be the one, at least if I am not wrong, the vertical axis driven with the impeller rotating in the horizontal plane, impeller rotates in the horizontal plane. Again, we are not going to go into details, pardon me. So, other one is, as I mentioned, the Archimedes screw pump. As you can see, as this Archimedes pump rotates from around this height, the water is being brought up to this height. So, depending on the speed or velocity of rotation, let us say your water will be taken up to this particular head, and that is what you see Archimedes screw pumps, let us say, right. The open impeller screw picks up and lifts the sewage, right. Depending on the speed, obviously the quantity lifted varies. There is, as you can see, there is no piping or walls, and the material is carbon steel and relatively less maintenance, but again always pros and cons with respect to the flows. And next aspect is how many pumps do I need to put in. So, here note that we were talking about, let us say, 30-year design period, and we were also talking about peak factor, 2 hour maximum flow, or 1 month maximum flow, and so on and such. So, if I just have the pump, what do we say, designed for just the average flow rate, during the peak flows and such, the system is going to fail. So, how do I take that into account? So, we take it into account by seeing to it that even with the largest pumping station, what do we say, disabled, offline, disabled, under repair, the system can still handle the peak flow, right. So, that is something to keep in mind. There is always going to be a fallback option. So, we are going to look at two aspects. Again, this is the reference CPH-EEO, and we are looking for small capacity here and then for large capacity pumping stations. So, we have 3 pumps here, and DWF stands for the dry weather flow. That is something that we looked at in the earlier session. So, one pump will be of capacity that can handle the average dry weather flow, and one of a capacity that can handle 2 times the dry weather flow, and one pump that can handle 3 times the dry weather flow. So, overall 3 pumps with increasing capacities, and here we have 5 pumps for the larger pumping station, right. And again, what do we have here? The 2 will be of half, such that they can handle half the dry weather flow, right, and 2 will be such that they can handle the dry weather flow capacity by themselves, right. Each one will be able to pump up the dry weather flow capacity or has the capacity to pump up the dry weather flow by itself, and one will be of 3 times the dry weather flow capacity, let us say, right. So, here you see that we are trying to choose it in terms of DW flow or dry weather flow, right, and then 100% standby we are providing for the peak flow, as I mentioned earlier, and then it is going to lead to easier inventories and such. And then this setup, it is possible such that we do not need to put in the pump installation till the volume increases, as in I am what do we say, building my or designing my sewage treatment plant for what is it, a 30-year period. But right now the population is less, but that does not mean I should not start the sewage treatment, right. So, in this setup, as you see, you can keep increasing the capacity as and when the flow increases or is estimated to increase, rather than having all the capital being spent right away and thus incurring costs, let us say, right. So, that is one aspect to keep in mind. And what is the head required that you need to pump up the water to? So, total head is the static head, for example, inlet is coming here, outlet is going here. So, let us say static head. The other one is there will be losses due to pipe friction and also losses in the fittings. So, these are the aspects that you need to take care of when you are trying to look at the total head, right. The total head will have to take care of the static head and also the losses due to the pipe friction and what do we say, losses in the fittings, right. Pipe friction loss, but again we are not going to go into that in detail now. So, flow measurement. Firstly, why do I need to measure the flow? Why is that? Because if I do not know how much flow is coming in, how do I know how much microbes to be maintained in the system? How do I know how much oxygen to pump into the system? Because if I keep pumping oxygen at the same rate, even if the flow is less, I am wasting money, because pumping costs of oxygen are remarkably high, or not most probably, they lead to they take up almost 50 or 45% of the total operation costs of a sewage treatment plant, right. They meaning pumping oxygen into the wastewater. And if I keep it constant, when the flow is high, I am not providing enough oxygen, so the process efficiency is going to decrease, right. And let us say I am talking about disinfection. If I do not know the flow, I do not know how much to pump in, right. or how much disinfectant to add and such. So, obviously, I need to know the flow. So, that is one aspect to understand. And where do we have? Typically, we have it downstream of the bar screen, sometimes downstream of the grit chamber too. It depends, right. Certainly, you are going to remove the bigger or coarser what do we say particles, certainly the much bigger particles, plastics and such, so that they do not choke your pump sets, let us say. And pardon me, I guess this is with respect to flow measurement, right. I got that slightly wrong. So, we will have that downstream of the bar screen and the grit chamber typically. When I spoke about having it after bar screen, but before grit chamber and such, I was talking about the pumping station, right. So, you can have this flow measurement in the rising mains of the pumping station, but that is possible due to the magnetic flow meters. We will just discuss that now, right. So, flow measurement, Mr. Parshall, right, his particular theory which is working remarkably well. So, we construct what is called a partial flume, that is what you see out here. For this, obviously, you need to have relatively longer distance or considerable distance depending upon the width of this particular flume, right, for the creating the relevant flow conditions out here. And also downstream also, depending on the width, you need to maintain some conditions so that the backflow conditions do not affect your what do we say flow conditions through the flume, right. So, you need to have considerable what do we say lengths that you can provide, let us say, right. So, what does this consist of? Let me look at the figure. Okay, this consists of a converging section. This is the water coming in, right. This is, I guess, the top view, and then transition. So, converging section, and then throat, and then diverging section, right. So, what is the need here? Why am I trying to vary the flow and such? Because here I am trying to measure the flow rate Q. Q is V times A, velocity times the cross sectional area, right. So, then I will get the volume per time, that is what I am trying to get. So, at what do we say subcritical or such flow, the velocity is not really proportional to the height of your particular flow. But at critical flow depth, the energy is minimized and there is a direct relationship between the depth of the water and velocity. That is why I want to construct this partial flume, so that I can achieve critical flow conditions or supercritical conditions out here. Here it is subcritical, here critical or supercritical, and then again subcritical out here, let us say. So, I want to be able to come up with a way such that the flow at that particular point is proportional to my particular what do you say the depth of that particular flow is proportional to the velocity of flow. So, that is why we are constructing the partial flume, right. So, what do we have? Consists of a throat, converging and diverging section. Constructing the width, that is what we saw, this is the width is decreasing, and raising the bottom, right, raising the bottom, I think that is not clear from here, right, causes flow to change from subcritical to critical or supercritical. One depth measurement gives the discharge, right, and more importantly it is supposed to see to it that it is self cleansing and there is little head loss, let us say, right. And we are going to convert the depth readings to discharge using a calibration curves. It is not greatly accurate, but it typically does the job within this level of accuracy, right, and that is something we just discussed or looked at. Flow is coming in, and here is where we have the critical flow conditions, and you are going to measure the head here, and then you are going to measure the head, relate that to the velocity and get the flow rate, let us see, right. Here, how are people measuring the head or the depth, pardon me. So, they have an ultrasonic source, I guess, and transducer to capture the reflected signal, ultrasonic source and a transducer to what do we say capture the depth. You can see the varying depth out here. So, elevation of wastewater in a flume is measured ultrasonically here. Some earlier or here you see a standby where you see the manual scale, if I may say so, where you have to manually record the readings, but obviously that is not going to be instantaneous, you have errors, and obviously people you have to depend upon the relevant person out there, right. So, flow measurement, the another aspect that we have is a magnetic flow meter, right. Let me just look at the relevant video here with you, right. We do not want to chat with anybody. So, magnetic flow meters typically do not require as much distances before and after, certainly not after. right, and they can be done inline in pipes and such. That is why we saw earlier that in the rising mains too, looks like you can have this magnetic flow meters, let us see, right. So, let us see what this is about. What do we have? We have a transmitter and a sensor, but what is it that we are transmitting and what is the principle? Let me see if I can keep up with the video. So, we have this magnetic, okay. So, what do we have? We have a transmitter, and we are trying to create a magnetic field. It depends, this particular principle is depend upon or uses the Faraday's principle, right. Let me just try to go through, and here we are trying to create the magnetic field out here, and then you have the relevant electrodes at the side. So, once you are creating the magnetic field, what is going to happen? The charged particles in the water are now going to be, what do we say, I should not say used to the go to the opposite ends, right. So, negatively charged and positively charged, they are separated. You have a potential difference, or here let us say, or difference, and this voltage you can measure. So, with the magnetic field you can now create conditions such that you can measure this difference or the voltage, let us say, right. And let us just look at that Faraday's law. Okay. Velocity, and what is it proportional to? As you see, it is proportional to the velocity of the process fluid. And what is the conductor? The conductor is the sewage itself, right, and we know the magnetic field strength that we are maintaining, right. So, that is how we can go through that. Distance between the electrodes depends upon the kind of system that you have. The induced voltage is what you are measuring out here, right, induced voltage due to the magnetic field, that is what you are measuring, and that you can relate to the velocity of the process fluid, right. So, that is something that we have, the others are constant for a particular system. So, that is more or less the case for your magnetic flow meter, right. Enough of that, again Faraday's law, right. So, let us move on. So, inline magnetic flow meters work on the principle of electromagnetic induction. Induced voltage, I guess we already discussed this, but you can look at that as and when requires. And what is the conductor? The conductor here is nothing but the sewage itself, right. So, what have we looked at until now? We looked at pumping the water up, we looked at measuring the flow of water, and now we will also look at how to measure the, not measure, remove the bigger particles and what do we say, junk that come into the wastewater, so that they do not mess up my downstream unit process, right. Let us see what we have out here. So, we have what we refer to as bar racks and screens. So, we are going to look at the screening out here, right. What is it that it is trying to do? Protecting the process equipment, obviously that is downstream, and it prevents interference with treatment, and also obviously we do not want it to be discharged into the streams or the rivers. So, screens we have different kinds, coarse screens which are always employed, fine screens which are not really employed in wastewater treatment, at least not in India, because the maintenance is high, and micro screens too in India we do not really, or people do not really go for them, certainly not micro screens. So, coarse screens earlier they used to have manual or hand cleaned, right, and now most of them are mechanically cleaned, chain driven, reciprocating and such continuous belt, but we will just look at the pictures and move forth, right. So, what do I have? I have front and chain driven, right. You have this coming in and going forth and the flow going through in this process, and you have racks or such which we are going to look at. Let us say you have the bar racks and such out here, let us say, right, and here is the collection trough where the relevant what do we say, particles or material that is screened out is what do we say, collected. And then we have this reciprocating rake, right, and that is what you have out here, and different such mechanisms. What do we have? Catenary and continuous belt, right, catenary and continuous belt, that is what we have out here, right, general operation. And let us see, this is the manual screen, manually cleaned bar rack in a very small plant, right, just easy to maintain, so that you guys can see the kind of particles that they were trying to capture. A commutator which was used to pulverize, but it is now not functioning, I guess, right. So, that is something to keep in mind. But mechanical screens, and now this is a picture from India which I got from Dr. Kazmi. You can see what kind of junk comes up. The other picture was from the US, and this is what you see, again mechanical screens now, right. You see the kind of junk that we are trying to remove out here, right. So, that is something to keep in mind. So, I think they have a combination of manual and mechanical screens out here, right. So, front cleaned, front return, chain driven rack, right. So, that is the picture that we saw out here, okay. This one, this kind of one, right. Again, also variations of it used widely in India, right. This is what you have. And what is it now? If I install it out here, now it is installed out here, as you can see, the continuous belt bar rack, and the water is coming in this direction, right. And you can see the continuous belt operating, it is all covered now, and it is covered, or the waste is being collected out here, let us say, right. So, you can see the kind of waste that is being collected in this from the back of the bar rack, right. And that is in India we see much more different kinds of waste, but this was from a relatively more developed country where the sewerage network and the kind of waste that comes in are relatively more controlled. That is something to keep in mind. So, mechanical, and in mechanical screening we also have drum screens. Again, this is where we are looking at relatively finer particles, right, depending on the size of this particular pores in this screen. But again, as I mentioned, in wastewater plant, people typically do not go for that. Depending on the waste or your design, you might want to. Again, the issue is because the maintenance is high, but again, mechanical screens, front end and such, and manual out here, right, front end and manual. So, screen design, one aspect is the velocity should be above a particular threshold. Why is that? Because in this particular location, you do not want the grit to deposit. So, you need to have relatively high velocity though, but the velocity should not be so high such that these particles or the probability of these particular material being captured on the bar racks is less. So, it is a balance between a particular velocity, so that grit does not deposit, and higher threshold, so that these particles do not escape. And then when you are going to have to design, you have to look at these parameters, but we are not going to look at that in detail now though, again not in an UG class anyway. So, grit removal, when I say grit, right, what is it that I am talking about? We have sand coming into the picture, dust, bone chips, coffee ground, seeds, eggshells, right, which are usually heavier than or much heavier than organic matter, but which are relatively inert, let us say, right. What do I have out here? So, this is typical grit removal or grit, let us say, you see the outlet here, right. So, let us move ahead, and this is from a relatively more developed country where they looked at grit and then screenings later, let us say, right. And reasons for removal, why do I need to remove? We will look at the pictures. To protect the moving equipment and pumps from unnecessary wear and tear, because that will lead to high maintenance. You do not want your pipes to be clogged up. As in recently we had an MTech student who was trying to divert the flow from, what do we say, the residents outside IIT Roorkee. There was a particular colony and he wanted to use that for a particular pilot scale wastewater treatment plant. And MTech, typically the thesis here at least is done over 1 or 1.5 years, and in that period he spent around 9 months trying to unclog the relevant pipes and such. Why is that? Because a lot of plastic rags and such always comes into the issue. So, again not just plastics and then grit, and that leads to relevant issues and maintenance. That is what I am trying to or was trying to stress upon when I was giving the example. You have a lot of issues with respect to maintenance and downtime, and you want to prevent that, right. So, that is what you see. And preventing cementing effects on bottom of sludge digesters. Bottom of sludge digesters, you can remove the sludge, but if it is these kinds of particles which end up almost forming a solid layer, your effective volume will decrease, and that is what we looked at. Inert material deposition, you want to prevent that, and aeration basins, right. So, what do we see? We see this, right, nuisances in aeration basin and sludge digesters, right. All this is because they did not have good grit removal systems upstream. In their aeration tanks and sludge digesters, they now have all this grit that has accumulated, right. So, that is the reason. So, design goal, what are we trying to do and such, not what, how are we trying to do that? We want to provide sufficient time, which I am going to call as detention time, for the grit to settle, right. Here again gravity or different separation process while maintaining constant velocity to scour the organics. So, the issue here is that I need to see to it that the particle that comes in settles down before it goes out, let us say, right. That has to be achieved. So, for that I need to maintain a particular velocity, let us say, which is greater than settling velocity. If the, what do we say, settling velocity is this, if V is greater than Vs, the particles will be removed, if not a fraction, but we will look at this type 1 settling later. Type 1 settling, which is discrete settling. As in this kind of settling, we are not concerned with interactions of one particle with the other within that particular system, right. So, that is something to keep in mind. But the assumptions are that the velocity is constant in this system, and we assume that it is a plug flow reactor. That is something that we mentioned and discussed earlier, right. So, there are some assumptions that we have to make, at least in this case. Again, type 1 settling, we know the Stokes law, and that will let you get an idea about the settling velocity. Again, how can we get that? We know that due to gravity it is going to be pulled down, gravity, but there will be drag resisting this, and also buoyancy, let us say, right, buoyancy. So, if you balance these out and look at the relevant calculations, you will get the settling velocity, but again we will look at this in greater detail soon when we look at sedimentation. But for now, when we are trying to look at the removal of grit via settling, these are the principles, let us see. What is it? That we are providing sufficient time for grit to settle, okay, while maintaining constant velocities to score organics. So, one is maintaining sufficient time, part A. The B part is that I do not want my organic content, some of which is suspended, right. I do not want that to be removed now, because this grit, right, is inert, right. Sand, if I dump it out there, not really a lot of issues or such, let us say. But if I have organic content that is dumped out there, I need to look at its disposal, its treatment, right. So, I do not want to club these two together and remove them. Why? Because what I do later is also depend upon the kind of particles that I am removing in that unit process. So, the velocity has to be such that it is low enough for the particles to be these heavier particles to be removed, but high enough such that you have a scouring what do we say, velocity, let us say. Even if the organics settle down, the velocity is high enough such that they can again be scoured up and they can be taken out, right. So, that is something to keep in mind. So, two aspects out here, and here we need to calculate the surface overflow velocity or surface overflow rate, let us say. How do we do that? Let us just look at that surface overflow rate or such. Here let us say I am just trying to calculate the h or height required, right, or height. So, if I am trying to look at that time by detention time, right, what will this give me? It will give me the velocity in this particular direction, if I may say so. Here I have this h, let us say, right, or let me use the term capital H, right, h by time. But this time is governed by how much flow is coming in and what is the volume of this tank, right, h by. So, I am going to look at the velocity here, right, and this is height h, let us say, and now I have this detention time. But what is this time depend upon, or what is this going to give me? It is going to give me the time that this particle or water too is going to stay in that particular tank. So, it is going to be depend upon the volume, right, V, this is volume, by the flow rate, right. Let me just write that out here. So, that is going to be the height, volume is length into breadth into height by flow rate. So, I will take this Q up. So, let us try to simplify this further, h cancel out. So, I have the Q and length into breadth, right, h is the particular depth. So, this is called the overflow rate, let us say, right, and this is something that I need to consider when looking at which particles will be removed and such, or let me not use this term, overflow velocity or surface overflow rate, right, surface overflow rate, right. So, that is something to keep in mind. So, let us move on, we will discuss this in detail later. So, design of grit removal, grit chamber may be designed assuming that it is a sedimentation basin. So, particles are treated as discrete particles, that is why we said discrete settling or type 1 settling with their own settling velocities. and obviously the velocity of settling of each particle will be dependent by the size and gravity of the particles, right. And minimum size and such, we discussed this out here, but we can move on. So, we have this long, I mean the flow is in this direction. As I mentioned, constant flow velocities have to be maintained, and how do they do that? They do that by using either the proportional flow weir, as you can see out here, the reflection is seen in here and the exit is seen or from the other direction, this is what you can see, or the Sutro weir, I guess, right, that is what you see out here. Again the point is to maintain constant velocities even at different flow rates. What do we have here? It is the flow rate here, million liters per day at different heights, let us say, right. And proportional weir, I think we have a close up out here, different velocities and such. So, without water, this is what obviously it looks like. Again, what is it? As the particle travels in this direction, right, you know the h for different what do we say, flow rates, and then if your velocity of settling is greater than Vs, then the particle will be removed, let us say, right. So, that is something to keep in mind. So, let us move on. If not, if you want to look at more compact systems and such, or you want to also look at better removal in a way where it is not dependent upon the flow rate coming in, you will look at this aerated grit removal, where by pumping air in, right, say, right, you are going to pump air in to create this, what do we say, spiral flow path for the relevant particles, let us see. And because of that, again your particles, heavier particles will be settled out or removed at the bottom, let us say, the trajectory of the grit particles, right, they will be removed at the bottom. Let us see if we have a relevant picture out here. In aerated grit chambers, we are letting the wastewater flow in a spiral pattern, and how are we inducing this spiral pattern? By introducing air along one side, let us say, right. Heavier particles are accelerated and diverge from the streamlines, that is pretty much straightforward. Let me see what I have. Okay. So, diffusion header, air is coming in here, let us say, and you are trying to create this condition, right, and the heavier particles, they settle down out here, let us see, suppression zone, yes, and this is how air is being let in, yes, that is something to keep in mind, and the grit or the heavier particles will obviously be collected out here, let us see, the air is coming in and it will create that spiral motion. So, what are the advantages? Let us just look at that. Over a wide flow range, you will have consistent removal efficiency, right, because it is mostly dependent upon the spiral action or the air that you are pumping in. So, some organic content may be removed with well controlled rate of aeration. So, you can start organic or degradation earlier, but obviously microbe concentration is less. Performance of downstream units is improved or can be improved to reduce septic conditions in incoming wastewater. Why is that? Because here we are pumping in air contains oxygen, right. So, that is one aspect. Aerated grit chambers are versatile, allowing for chemical addition or mixing, pre-aeration, which is the key, let us see, right, and sometimes it allows for flocculation, right, that is one aspect to keep in mind. But obviously, the area is relatively higher, but higher compared to, again this is the relevant what do we say, spiral or aerated grit chamber. These I guess should be the air diffusers, let us say, right. Let us look at that compared to what is this aerated grit removal, relatively bigger, it is compared to the vortex flow grit remover, but again we will just look at that. I am almost at the end of my session. So, here what is the HRT that we are trying to maintain? It is 3 to 5 minutes, and the relevant dimensions or the design parameters are given. Being a UG course, we are not going to go into that, but retention time, as you see, is not high. Hydraulic retention time, as in how much time is my water, hydraulic detention time or retention time is it spending in the relevant system, it is not high, 3 to 5 minutes. And another aspect or way, but with a much lesser footprint, is the vortex grit removal chamber. Again, what do we see out here? It's water is fed tangentially, and you have these rotating turbines that create this spiral flow, right, and then grit movement pattern along the outer edge of the unit. So, grit will be collected and then it can be removed in this way, and then the outlet is out here, and the outlet chamber typically is going to be at a relatively, or almost twice the area of the inlet, right. Why is that? Because you want to have low velocities at the outlet such that the grit is not carried through, right. So, that is something to keep in mind. So, let us just look at the main points. Influent fed tangentially, you want to have the vortex, right. Paddles are used to maintain the rotation velocity. Circular and conical shapes, obviously, right, to reduce turbulence and maximize grit settling, right. Let me move on to the relevant pictures. So, inlet and outlet, I think I have a better picture, but here we see the relevant shapes corresponding to the relevant what do we say, location in the vortex unit. Optional air or water scour fluidized bed prior to grit removal, right. And here we see the inlet coming in tangentially, and as I mentioned, the area of your outlet is typically twice that of the relevant inlet, let us say, right, and from a different angle. So, here is the inlet coming in, and this is the vortex chamber. Here is the impeller, if I may say so. Again, this is still under construction, and here you will grit will be collected out here, and your outlet is out here, let us say, right. That is the same picture that we looked at earlier. Once it is fully constructed, coming in, right, grit discharge line from the center, right, and effluent channel is going out this way, let us say, right. So, as required, if the flow conditions require it, the bypass, right, that is something that you see. So, typically there are also compact units, but the issue with this vortex what do we say, grit removals is that unlike the aerated ones or such, here they are relatively what do we say, not relatively, they are proprietary, as in you need to typically buy them from a company and such. So, obviously costs are going to be an issue, and if you buy it from a company, the maintenance is dependent upon the relevant person and such. But here obviously with respect to the vortex one, the costs of maintenance are less because you are not really aerating it, right. In the aerated one you need to pump in a lot of air, yes, but here you have your own disadvantages. So, you need to look at which one to choose, let us say, right. So, with that, thanking you for your patience for a marathon session, I will end my session for today.